There are two things that we look for when we're trying to work out whether a molecule is polar or non-polar. Firstly, whether the bonds are polar, and then about the shape of the molecule. First up, polar bonds and non-polar bonds. So when we have a covalent bond, it's sharing electrons, right? So if those electrons are shared equally, we have what's called a non-polar bond. The electrons are shared equally when they're pulled equally by the different atoms. So in this case, we've got two oxygen atoms. They pull electrons the same because they're the same atom. This word, the word we use for the pull of an atom on its electrons is electronegativity. How much does it hog electrons? Because these are the same, they share the electrons equally. So that means that there's no positive or negative end because the electrons are equally shared between the two atoms. On the other hand, if we look at something like hydrochloric acid, HCl, the chlorine is more electronegative. It's more of an electron hog than our hydrogen is. And this means that the electrons are clustered down the chlorine end. And what we get from this is a slightly negative charge because there's more electrons down there. And we put a little delta negative down there, and this is our negative dipole. And on this side of the bond, we will have a positive dipole, a delta positive. And that's because comparatively, there's less negative charge down that end. So that's about bonds. And you can see here I've characterized bonds as, if they're red, they're your polar bonds, and if they're blue, they're your non-polar bonds. So most of these, because they're different atoms, they have different pull on the electrons, are polar bonds. Okay, so that's not enough to make a polar molecule. So let's have a look at this polar molecule, or this non-polar molecule down here. The interesting thing about it is that it has polar bonds. There's a difference between the electronegativity of carbon in this methane molecule and hydrogen. So carbon pulls the electrons a little bit more, it's slightly negative, and the hydrogen is slightly positive. And that's the same for each of these around this tetrahedral molecule. Because this molecule is symmetrical, there's no particular side that's different. And yes, there is a positive charge on each of these hydrogens, but there's no particular side of this molecule that is more positive than the other. That means overall there's no dipole. So it's what we call symmetrical. And this means that the charges cancel out, and so it's non-polar. So there's no part of this molecule that has a pole, a dipole, a part that's slightly more positive, at least from the outside. So obviously the inside, which we can't get at and which isn't sort of chemically available, is more negative, but around the outside it's kind of homogeneously positive, all the same. On the other hand, if we have a look at our ammonia over here, our nitrogen is more electronegative. It's more of an electron hog. That means we have a delta negative up there, and for each of our hydrogens, we have a delta positive. Delta positive and delta positive. This means that overall, there's a side to. So if we have a look at our nitrogen, our ammonia atom here, our ammonia molecule, we can see that there is it's not symmetrical in the same way. if our nitrogen has a negative dipole, then we can see that from the outside we can kind of access that. And we'd write this like this. So we can see that towards the hydrogens there's a positive side, right? And that goes up to my negative dipole of my molecule as opposed to just the bond. So that's the difference. So these are all polar bonds, and you need polar bonds in order to have a polar molecule, but that's not enough. It needs to be asymmetrical, so not symmetrical around the outside. A good example of something that is asymmetrical but is actually non-polar is this ozone, this O3 over here. And the reason it is not a polar molecule, even though it's not symmetrical, is because it doesn't have polar bonds. It has non-polar bonds because of the similar electronegativity. Thank you. Hope that helps.